Yeah, thank you very much. Yeah, okay, we see the date and the recording. So we will discuss two topics, external uses of Hasty Matrix and a little bit of past exams, because basically we have covered all the topics we need. Okay, and example, optimization used in statistics. We have n random sample of n observations, y1, y2, yn. They are independent. They are normally distributed with mean mu and variance sigma squared. And the first question is to just find the maximum likelihood estimator. And basically that means we need to optimize something. And the second question, calculate Hasty matrix at maximum estimators. It seems that what we can do with this Hasty matrix, we can check whether we have obtained minimum, maximum, but that's not only the main. So the main role of Hasty matrix in statistics is not limited to just find whether we have maximum or not maximum. Yeah, the main use is to estimate standard error of mu and estimate standard error of sigma squared. And then let's pretend that we have a lot of observations. Let's pretend that, I don't know, n is 1,000 or 2,000, let's say 1,000. We have sum of yn is equal to, I don't care, 2,000. Sum of y squared will be, it will be like 12,000 is sufficient. Yeah, I think it's, well, yeah, I think it's sufficient. Okay, and my question is to provide asymptotic confidence interval for mu, asymptotic confidence interval for sigma squared. Let's say the confidence level 95%. And then we will see that Hasty matrix plays an important role in answering point C and hence point D. Okay, Hasty matrix has in this problem a double role. It serves us to judge whether we have really found a maximum, and it serves us also to obtain standard errors. And if we obtain standard errors, yeah, we can build the asymptotic confidence interval. Okay, let's go.
Yeah, let's go.
Okay, so what we need to maximize. So basically, the function is hide it. Yeah, here we don't see explicitly the function. So we need to write the function we need to optimize. So maximum likelihood says that we need to maximize what? What we do need to maximize in the method of maximum likelihood, what we are maximizing.
Likelihood function, which is a product of the PDFs.
Yeah, exactly. We maximize joint PDF, or we maximize joint PDF. And if we assume that our observations are independent, then you're perfectly right that we need to optimize a product of PDFs. That's not the case in general, because when you, for example, use maximum likelihood for time series predictions in time series, y1, y2, and so on are dependent, but that's not the case. In these problems, y1, y2 are independent, and so we really, you're completely right, we maximize the product. We maximize the product of individual marginal densities. Yeah, we maximize with respect to mu sigma product I ranging from I to n f of y number I given parameters mu and sigma squared. As always, it's easier. That's interesting that it's easier not only for humans like we, but also for computers. It's easier to optimize not this product, but logarithm of this product. Why it's easier to maximize logarithm of this product and not this product itself? Why it's easier to go to the problem maximize mu sigma squared logarithm of this product? Why it's easier?
Because we obtain a sum.
Yeah, it's a question for humans like you and me. Yeah, because logarithm of product is sum of logarithms. Yeah, you are completely right that for humans it's easier to work with a sum than with a product. Yeah, but why so for computers? Why it's this change of goal function is useful, very useful, even on computers? Why so?
Well, when computers, just like humans, work with sums, they need to collect to keep less data in the mind. No.
In real life applications, the function is very complex. You cannot find extremum explicitly, and so some numeric algorithms are used, like gradient descent or stochastic gradient descent. So computer optimizes the function not using ready-made formulas, but he starts from a point, he moves in the direction of a gradient, and he recalculates gradient, moves in the direction of a new gradient, and so on. And basically, because computer can do calculations very fast, then it moves and obtains better and better value of goal function. But for computer to calculate product of n numbers or to calculate sum of n numbers, what's the difference? If you look at the time needed to execute, that's a miracle, yeah. If you work with float point operations on a modern computer, and so it seems at first that maybe it's shocking, but for computer, float point operation sum takes almost exactly the same time as a product. Computer will not multiply 5 by 10 by adding 10 5 times, so by adding 5 10 times. So the time of float point operations for multiplications and for additions is almost the same on modern processors. So that's not the reason, but we have a deep reason to work with logarithms of likelihood on computers.
Maybe because in this case we get simpler derivatives.
Okay, the answer probably is difficult, but if you look at this value, it's a product of some small numbers. So imagine you have 1 million or 1,000 observations. Each observation is let's say 0, 1. If you multiply 0, 1, approximately 0, 1, 1,000 times, then you will get 0, 0, 0, 0, 0, 0, 0, 0, 0, and oops, the result is out of float point precision, because you have limits for float point precision. So basically, if you just multiply 1,000 or 1 million small numbers, each number is around 0, 1 or 0, 0, 1. So, oops, you can just calculate using float numbers. And if you take logarithm of 0, 1 is, let me verify, logarithm of 0.1 is roughly -2. If you add -2, -2, -2, -2, 1,000 times or even 1 million times, you obtain -2,000 or -2 millions. That's perfectly a number within float point range. And there are no problems of precision when you work with logarithms. Because if you have 1,000 observations, each f is approximately 0.1, then the product of f is 0.00001. You have problems with precision. But if you work with sums, then perfectly okay. So all models that are really used in statistics or econometrics, they're always logarithm of density maximized. Okay, so it's not only for us, for humans, to work with sums to take to calculate first order conditions faster, but it's also for computers. That's a very beautiful fact that the way is very different. We are searching for explicit solution, but the recommendation to take logs is okay for humans and for computers. Okay, let's continue. Yeah, the idea of the problem without logs is clear. Yeah?
Yes.
Okay, let's move on. And now what is density? Yeah, you may, I don't know, Google on Wikipedia, or you may probably, I don't know what are the requirements for statistics course. Probably you know it, probably you don't know it. I will write it for you. So it's 1 over square root of 2 pi sigma squared, exponent minus 1 over 2 y minus mu squared divided by sigma squared. And if I take logarithm of this function, I will have minus 1 over 2 logarithm of 2 pi sigma squared minus 1 over 2 y minus mu. Oops, I forgot to divide by sigma squared. Yeah, that's okay. Maybe you know this formula, maybe you can just believe me. I'm not sure about the requirement.
It's okay.
Okay, so we just sum and we maximize, so we have maximization problem. Error optimization comes into play. So we take this function and we have minus n over 2 logarithm of 2 pi sigma squared minus, and here y is different, so I cannot multiply by n, but I can write the sum divided by 2 sigma squared, and we maximize this function with respect to mu and sigma squared. Okay, so now the statistics, the probability part is finished for the moment. So now we have purely optimization problem, but we will go back to probability when we will interpret Hesse matrix. So basically, our path will be like this: first a little bit of probability, but probability has ended. So now we have purely optimization problem, probability problem. Now we have optimization problem, and then when we will find out extremum, we will find out Hesse matrix, and we will go back to probabilistic interpretation because we have good properties of Hesse matrix. And that part is okay. Yeah, let's maximize it. What are the what are the let's write what are the derivatives of this function, dl with respect to d mu and dl with respect to d sigma squared. Let's treat sigma squared as a unique object. Yeah. What is dl d mu? What is dl d sigma squared? Who has calculated?
Well, with respect to with respect to mu, it's just sum of mu multiplied by 2 divided by 2 sigma squared. No.
Yeah. Here we have so the first part will disappear, and we will have 1/2 sigma squared sum of y minus mu. If we take dl d sigma squared, it's a little bit more difficult. We have minus n/2 times 1 over sigma squared. I think plus 1/2 sigma squared sum of y minus mu squared. Like that.
Wait, I guess in the derivative of mu, we should delete 2 in the denominator, no?
Yeah, you're right. Yeah, I agree. Yeah, you're completely right. I forgot.
In the second derivative, like in the first element, there is also like two mu in the numerator, because it's like logarithm of not mu, logarithm of sigma squared, so there should be 2 sigma at the top.
Ah, yeah, you here, yeah. Like that.
And in the first term, first element of the sum.
Of the first term, what do you like to write here?
So we have function logarithm of sigma squared, and
yeah,
when we differentiate it, so there is 1 over sigma squared.
Let me add some numbers. You are speaking about the first one, about the second one.
About the second. About the second equation, the first term of the sum.
Yeah, what's the problem?
So I think there should be 2 sigma at the numerator.
Why? I work with logarithm. I prefer, so
yeah.
Honestly speaking, what I do, I say minus n/2. That is logarithm of product, so it's logarithm of 2 pi plus logarithm of sigma squared. I know that when I multiply numbers, logarithm of product is sum of logarithms. That's a basic property of logarithms. And when I take derivative, this guy 2 pi will disappear completely because that's a constant. And when I take derivative, I will have minus n/2, that is outside the bracket. And I think I will.
Wolf, it's because we differentiate with respect to sigma squared, not sigma.
Yeah.
Oh, okay. Yeah, I see. Sorry.
So we may differentiate with respect to sigma. Yeah, I see your point. And the answer will be the same, but the derivative will be different. But the optimum point obviously will be the same. Yes, you're right. But I prefer to treat sigma squared as a unique object because in the end of the exercise, we need to build the confidence interval for sigma squared, not for sigma. Okay. Okay, so we can obtain extremum. So if we will write the system of equations, 1 over sigma squared hat sum of y minus mu hat equals to 0, minus n/2 sigma squared hat plus 1/2 sigma power 4 hat sum of y minus mu hat squared equals to 0. And so we need to solve this system. Basically, it's easy. The main probably difficulty that we have a lot of parameters from optimization, from statistics point of view, mu and sigma parameters, yeah. And from optimization point of view, mu and sigma are variables, and y1, y2, yn are parameters. Yeah, we will express mu hat and sigma squared hat in terms of y1, y2, and so on. So basically, that's a little bit different of a little difference in terminology. In statistics, we will say, oh, mu is a parameter. And when we speak in optimization language, we say that we optimize with respect to mu and sigma hat, mu hat and sigma hat. So mu hat and sigma hat are variables, and y1, y2, y3, yn we treat as given exogenously, and so we treat them when we optimize as parameters. But from statistics viewpoint, mu and sigma are parameters, and y1, y2 are random variables observed. Okay, so the first equation says that we have sum of y minus sum of mu hat is 0. And basically sum of y minus n times mu hat is 0. Mu hat is sum of y divided by n, or y bar. And that's pretty expected. Yeah, that is not a shocking result. Yeah, when we try to estimate mu, it's a good idea to work with just sample mean. Yeah, so it's not very shocking that the estimator of mu is y bar. Okay, now we can solve the second equation. So the first equation is solved. Now we solve the second equation. We multiply by, let's multiply by 2 sigma power 4. And we obtain minus n times sigma squared plus sum of y minus y bar equals to 0. And y squared maximum likelihood is sum of y bar minus y divided by n. Okay, any questions here?
That's clear.
Okay, now let's use Hasty Matrix first for optimization purposes and then for statistics purposes. Because maybe we have just found minimum, or maybe it's a saddle point, or maybe, okay, we have either maximum, saddle point, or minimum. Okay, let's check whether what we have obtained is indeed maximum. Okay, we need to calculate second order dl d mu squared, dl d sigma squared, we need to calculate the second derivative with respect to mu to sigma squared. And just to copy dl with respect to d mu, it was 1 over sigma squared times sum of y minus mu. Oops, sorry. And dl with respect to d sigma squared was minus n over 2 sigma squared. Oops, sorry. Yeah, sigma squared plus 1 over 2 sigma power 4 sum of y minus mu squared. Okay, we have everything we need to calculate Hasty matrix. What is dl with respect to d mu? second twice, dl with respect to d mu twice.
Minus n divided by sigma squared.
Yeah, if we take derivative, we will have a minus sigma squared times sum, and inside we will just have minus 1. And so it is n over, oops, sorry, plus, minus n over sigma squared. Okay. What is dl, the second derivative with respect to mu to sigma? So I need to take the derivative of the first expression with respect to sigma squared. So I will obtain minus 1 over sigma power 4 sum of y minus mu. And the most difficult, but let's be brave, it will be plus n to sigma power 4. Here I will have minus 2 over 2 sigma to the power 6 sum of y minus mu squared. Yeah, am I right?
I believe yes.
Okay, then we can evaluate Hesse matrix at the point we have. Let's evaluate if I plug in sigma hat, if I plug in sigma hat and mu hat, if I plug in mu hat. So now let's plug in the value we have obtained. So here I will have minus n divided by sum of xi minus sum of yi minus y bar squared divided by n. Yep.
Yes.
And it will be minus n squared over sum of y minus y bar. Everything is okay with the first one?
Yep.
Let's simplify that one. We plug in everything we have, minus 1 over sigma. So it will be minus n over sum of y minus y bar squared once again, because I have sigma to the power 4 minus sum of y bar minus 1. And it will be equal to what? The mixed second
0.
derivative. Yeah, it will be equal to 0. Why?
Because of the sum of yi minus y bar.
Yeah, of deviations. Yeah, deviations from the mean. This sum is exactly 0. Okay, and here I need to plug in. So I need more space. Let's continue. M over 2 sigma hat, 2 sigma hat power 4 minus 1 sigma hat to the power 6 plus times sum of y minus y bar squared. Okay, I will multiply by n twice and multiply and divide by n. And I see that I have n 2 sigma 4 minus n sigma hat to the power 6 times sigma squared, because that is just sigma squared. And I will basically have n over 2 sigma power 4 minus n over sigma power 4. And I will have a minus n to sigma power 4. And I may write it like minus n cube over 2 sum of y minus y bar power 2 outside. Okay, any questions? Or everything is clear?
Everything is clear.
Okay, let's write Hasty matrix. Hasty matrix is very simple. It's diagonal in this case. It is minus n over sigma squared, and here we have minus n over 2 sigma. I will a little bit write in a compact form where sigma squared hat is sum of deviation squared over n. Okay, I see that delta 1, so if I use second order deficiency condition, delta 1 is minus n over sigma squared hat, it's negative. Delta 2 is minus n over sigma squared hat times minus n over 2 sigma squared power 4, and it's greater than 0. When I have the first principal minor of negative sign and second principal minor of positive sign, then what I can conclude?
A negative definite matrix.
So yes, the Hasty matrix is negative definite, and my point is
Maximum.
yeah, at least local maximum. Yeah, so we have our point is local maximum. Okay, what we can say about whether it's global or not, maybe rather what we can say. Okay, we have unique local maximum. We have no other local maximum. Okay, because so either we have two possibilities. So to be strict on optimization point, so what we can say, we have one local extremum, one local maximum, but maybe the function goes to plus infinity somewhere. Yeah, so we need to check to understand whether this maximum is global or not global. So how can we proceed? So how can we check that the maximum we have found is global? Maybe there are no extreme at all. Global, I mean, local we have found already, but maybe we have problems with that global extreme. Oh yeah, let's look at the function. Yeah, and we see that. So how to check whether the extremum is global? That's tough in general. So because sufficient order conditions by Hesse matrix, they look locally. So what we can use in general? In general, we can use Weierstrass theorem, but Weierstrass theorem is not applicable in this case. Mu is not bounded. We have no bounded region. But in this case, everything is more or less easy because for every sigma, we obviously have unique optimum mu. Yeah, we see that from the viewpoint of mu, we have a just parabola. So when we fix sigma, the plot is parabola. So okay, for fixed sigma, we have a unique extremum. Yeah. But if we have a fixed extrema for every mu, then to judge, so I understand that probably on statistics course you are not going deep in the existence of global extremum. I understand that every subject something is done very rigorously, something is done less rigorously, and more, and we use more intuition or some guess or some beliefs. But for the moment, we are strict in optimization part. So I'd like to be precise why we have found the global extremum. So how to prove that it's global extremum? First, we see that, okay, let's go and prove that it's global. Global? So, argument one for fixed sigma, we have a function L of mu that is just a parabola. So we are happy to see that we have a unique extremum when we fix sigma. And then if you look at the function once again, minus n over 2 ln of 2 pi minus n over 2 ln of sigma squared minus 1 over 2 sigma squared times sum of y minus mu. And when we have obtained mu, when we have L of mu hat sigma, yeah, we have minus n over 2 ln 2 pi minus n over 2 ln sigma squared minus 1 over 2 sigma squared sum of y minus y bar. And then this function depends only on sigma, mu, L of mu sigma squared fixed. And then when we look at this function, L of mu hat sigma squared, and we see basically how it looks like when sigma will be very small, yeah. We will have which part will be bigger for big sigma and for small sigma. For big sigma, this part will be 0. This part will be very negative. Yeah, so for big sigma, we'll go to minus infinity. For small sigma, we will also go because of that part for minus infinity. And basically, we see that we have unique, so we need to calculate the derivative. Okay, but the unique sigma squared hat exists. Okay, so in our problem, we have, sigma squared, and that is L of mu hat sigma squared. So we have unique, global, and local maximum. Yeah? Everything is fine?
Yes. Yes.
Okay, so so optimization part of the problem is finished. So where we are, we had probabilistic part of the problem. We have optimization part, and now we go back. So that is done. That is okay, and that is probabilistic part once again. So we have a theorem from statistics that under regularity conditions, conditions, conditions for maximum for likelihood function, we can estimate the variance of our likelihood estimators like minus inverse of the Hesse matrix at the extremum point. So basically, and this estimator is consistent. This estimate is consistent. So basically, what it does say, this theorem, it says, oh, if you have a matrix, if you take inverse of it, then you will have estimates of variance, and you can construct confidence intervals. So this theorem basically says that Hesse matrix is very useful. If you have calculated Hesse matrix, then you have calculated the precision of your estimation. Okay? Everything is clear, or the statement? Okay, we will not delve into the proof. Is the statement of the theorem clear?
Yes, it's clear.
Okay, so what we need is to calculate minus inverse of Hesse matrix, or inverse of minus Hesse matrix. Obviously, inverse and multiplication by -1 can be done at in different sequences.
I'm sorry, and is it covariance matrix?
Yeah, it's covariance matrix.
Okay.
Yeah, you denote it differently. I'm used to
No,
denote.
no. I just to clarify. I mean that we have.
Yeah, because we have. So this statement works in scalar case. In scalar case, it would be estimate of variance. In a two parameters or many parameters case, it will be a covariance matrix. Yeah, you're right. That in our case, we have a 2x2 matrix, and if we invert a 2x2 matrix, we will have a 2x2 matrix, and it's a covariance matrix estimate of covariance matrix. Yeah, you're right. Yeah. So you're right that it's a variance in scalar case, estimate of variance in scalar case, and estimate of covariance matrix in vector case. Yeah, you're completely right. That's a good point. Okay, let's calculate it. We have a matrix. We can find an inverse of it. That's not a problem. So even these two lines at the end of the page are sufficient. We have Hesse matrix. It was like, as far as I remember, mine. So it was 0, 0, was minus n over sigma squared, and it was minus n over 2 sigma squared to the power 4. Yeah. As a matrix at our point mu hat sigma squared hat was like that. Yeah. Am I right?
Yes, you're correct.
Okay. So our vector, so we work indeed in a vector case. Our vector is a vector of 2 parameters. Yeah. And the variance of my vector, the covariance matrix of my vector, I need to multiply by -1. Okay. And if I invert the matrix, how we invert the diagonal matrix? So if we have a matrix like that, 5, 0, 0, 7, how to find an inverse of a diagonal matrix? It's very easy. How we find an inverse of diagonal matrix? What we need to do to find inverse of a diagonal matrix?
Well, here it's 2 by 2, so we can do it shortly. It will be 1 over the product of diagonal elements as a scalar in front of the matrix, and then we switch the places of the elements on the main diagonal.
All right, but maybe it's a good moment to find out that diagonal matrices behave like a constant. You can inverse element by element. That's like a lazy student wish how to inverse a matrix. So, oh, it would be better to invert every element. Okay, we invert every element, because if I will do like you say, I will take 1, 7, I change the places, 7, 5, and bingo, you just like invert the diagonal elements. You will have 1/5 here and 1/7 there. You just invert diagonal elements when you invert a diagonal matrix. So basically, that works in general, not only for 2x2 matrices. So it's so if you have a matrix like 5, 7, 6, this is A, and you'd like to find an inverse of A, it's a dream. 1/5, 1/7, 1/6. It's a dream. You may try to multiply 5, 7, 6, 0, 0, 0, 0, 0, 0 times 1/5, 1/7, 1/6. And if you multiply, first line is multiplied by first column, you get 1. Second line is multiplied by second column, you get 1. Third line is multiplied by third column, you get 1. And you have zeros otherwise. Okay, diagonal matrices are easy to invert. That's a dream. It's easy to calculate power of diagonal matrix. It's easy to calculate, because inverse basically is the power of diagonal matrix. Okay.
Yes.
Yeah, so we have a estimate of covariance matrix of our vector of parameters. It will be sigma squared over n, 0, 0. Probably you recognize that guy. Probably you recognize that guy from statistics, and the other guy, probably you don't recognize it. Sigma squared hat over Q over n. Yeah, like that. The second one. Yeah. Or if the connection is lost, I'm not sure. Everything is fine.
Yeah, we can hear you.
Okay, because it seems in HTTP network sometimes is. Okay, let me reconnect to. Okay, it has reconnected on computer. Okay, so basically, probably you recognize that guy, yeah, that the variance hat of mu hat is sigma squared over n, because basically mu hat is what is y bar, and it should be divided by n here. Okay, so probably you recognize that you have proven that in statistics or in probabilities that the variance of average is 1 over n, variance of each term. Yeah.
Yeah.
Okay, but here Hasty Matrix is smart enough to know that without any statistical theory. Okay, Hasty Matrix has this result inside. And variance hat of sigma squared, that's not so trivial. Yeah, variance hat of sigma hat is equal to sigma hat over n. Okay, so it's an estimate of variance of sigma squared hat. And that's more difficult. So here, this result is less obvious. So maybe this result is more or less obvious. I can obtain it easily without Hasty Matrix. So this is easy without Hasty Matrix. but this is not obvious without Hesse matrix. Not obvious without Hesse matrix. So my idea is that Hesse matrix is a useful thing. Okay, and now standard error of mu hat is just square root of variance, yeah. Square root of variance, it's sigma hat over sigma of n, and standard error of sigma squared is a square root of that guy. It will be sigma squared over square root of 2 over n. And basically, because we know that asymptotically, so these intervals are asymptotic, so that's not for n equal to 20, that's not for n equal to 5, yeah, but asymptotically for big values of n, and as far as I remember, we decided to have n equal to 1000. Sum of y was 2000, and sum of y squared was, as far as I remember, 12,000. Yeah, I have provided that numbers.
Yes.
Okay, if we work with asymptotic results, we can say that maximum likelihood estimators are asymptotically normal. So, mu hat minus mu divided by standard error of mu hat goes in distribution to normal 0, 1. Sigma squared hat minus sigma squared over standard error of sigma squared hat goes in distribution to normal. So they are asymptotic normality of maximum likelihood estimators. And basically, these denominators, we have discovered them using Hesse matrix. Woohoo! Hesse matrix using Hesse matrix. That's a good point that we can basically have a confidence interval just for free. No long theory, no, you don't need to know properties of variance, of extended, just we have confidence intervals for free, for mu, for sigma, for anything else, but asymptotically only. If you'd like to have more precise confidence intervals in small sample case, then you need to know something about t-squared distribution and so on. But asymptotically, it's very easy. Hesse matrix and you win. That works only for big values of n. For small values of n, you need to know a lot of distribution like student distribution, t-squared distribution, f, and so on. But when n goes to infinity, Hesse matrix, and you win. Okay, so in our case, once again, the end of page. Let's be brave. If n is 1000 and sum of y is 2000, then we immediately conclude that y bar is 2, so mu hat is 2. Okay. We can say that sum of y minus y bar squared is just, we open the brackets, will be sum of y squared minus 2 y bar sum of y plus sum of y bar squared, and it will be 12,000 minus 1000 times 2 squared, and it will be like 8,000. And basically, we have estimator of sigma squared, y minus y bar squared divided by n, will be just 8. Okay.
Yeah.
Yeah, and finally, confidence intervals. Confidence intervals. No, standard errors. Yeah, that are estimates. Our standard errors is sigma squared over n is 8 over 1000 is 0.008. Standard error of sigma squared is 2 sigma to the power 4 over n. Yeah, as far as I remember. And it will be 2 times 64 or 100. It will be 0.128.
I'm sorry, should it be square root?
Yes, square root. Square root. Yeah, you're completely right. Yeah, I forgot square root. Let me find out. It's square root of 0.008. Yeah, you're right. It's approximately 0.09. And the second one is 8.036 approximately. And finally, I have asymptotic once again. Be normally distributed asymptotically. If I estimate mu, the estimator will be asymptotically normally distributed. I don't care which one, but asymptotically, I can easily build 95 confidence intervals. For mu, it will be from 2. So they have the same structure. If they are mu hat minus 1.96 times standard error of mu hat up to mu hat plus 1.96 standard error of mu hat. And the same for sigma squared. So if we like to work with big samples, then it's very easy. So it's very good approximation for big samples, but a poor approximation for small samples. So for small samples here, you will need t-distribution. In that case, you will need to change the structure, the formula, and work with t-squared distribution. So asymptotically, that's good. For small samples, they're all finite. For small samples, we will go to t-distribution, and t-squared and -1 will use. But that's not about. So I'm just like to focus on optimization. That Hasty Matrix is useful. My point, and that's not my point. Okay, and I have 2 minus 1.96 times 0.09 up to 2 plus 1.96 times 0.09 and 8. Yeah, it was 8 minus. So the structure is the answer asymptotically is the same. And that guy, basically, what is the origin of that guy? That's a square root of element of inverse of minus inverse Hasty matrix. Okay.
Yes, okay. And can we also use it as a proof that mu and sigma are independent or uncorrelated?
So it's an estimate. So it's so for a honest proof, no, because for honest proof, so yeah, you're right that in for this particular problem, you're right that they are uncorrelated and they are independent. Yeah, there is a theorem that in that particular case, if x1, xn are normally distributed with mean mu and sigma squared, then you are right that sigma squared and so you're right that sum of y minus y bar squared and y bar are independent. You are completely right. They are non-correlated. They are more, we can say more, they are independent. You're right, but that's not a proof because that about estimates. Our theorem says that we can, our theorem only asserts what I have used, that this is a consistent estimate. So this cannot be used as a proof of theorem you say, because we say that 0 is a good estimate of covariance. Maybe the covariance is very small and goes to 0. And in that case, 0. So in our case, this 0 is not, so you are right that we have 0 in our matrix, yeah, but that is not the true covariance. We use and treat the 0 as estimate of covariance of mu and sigma hat. This is the estimate of variance of sigma squared hat, and this is the estimate of variance of mu. So basically, you're right. It gives us a hint that mu hat and sigma squared hat are independent, but that's not a honest proof. Be careful. If you are required to prove the fact that mu hat and sigma hat square are independent, that this 0 in the matrix is not a proof, it's just a hint that they may be independent, but that's not a proof because it's only an estimate of true covariance. Okay, is it the answer for your question?
Okay,
or...
yeah, yes, thank you.
So basically, the mean of Hasty matrix is when you take minus Hasty matrix, if you inverse minus Hasty matrix, you have a good estimate of variance matrix, but it's not a true variance matrix. So you are right that the true variance matrix will be like that. In that case, yeah. If we consider, so we can calculate using some probability theory, we can calculate that the true variance matrix will be, in this case, the true variance matrix will be, you are right, 0, 0, sigma squared over n. And here I will have, just a moment. Will I have here exactly this without what will the variance? What will be the variance? The true variance. Just a moment. That will be a chi-square distribution. It will have a so and here the answer will be a little different. It will not be 2 sigma power 4 over n. There will be a correction factor because sum of y minus y bar squared over sigma squared as chi squared and minus 1 distribution. So its variance, the variance of this is I will have power 4. It will be 2 n minus 1 over n squared. So it will be a little bit different. It's a good estimate, but so if I just remove hat, I will not obtain sometimes an exact answer. Okay, so you asked me about the true variances, but our theorem about Hasty matrix is a little bit weaker than your question. The Hasty matrix say, I know about estimate. I don't know about true variance, but my estimates are consistent. And 0 is a good estimate of covariance. Okay?
Yes, okay.
Oops. So basically we have our time is up. If you have any questions, so my point is that Hasty matrix is a useful friend that may help you outside optimization. For example, you can estimate, build confidence interval, and I have a lot of observations in statistics. So I hope you are satisfied with this example. So see you next time. Have a nice.
I'm sorry.
Yeah.
I'm sorry. I have a question. So we were planned to do some exam task.
I'm always. I think the most.
Yeah, I just wanted to ask.
Which one?
Like which of the task you prepared? Like, whether you prepared any task or exam task, like.
Oh, I don't understand your question.
У меня уже голова немного, наверное, подвисла. Можно на русском спросить, короче? Мы планировали сделать задачу из экзамена, и вы планировали какую-то...
Можно, тем более, что помехи, я тебя плохо слышу еще банально.
Вот, вы планировали какую-то задачку с экзамена решать?
Я планировал что-то по оптимизации с параметрами, вот, я посмотрел какие-то годы, сейчас что-то не помню.
Ну, хорошо, ладно.
Ну, прошлого.
Да, хорошо.
Нет, какой-то, сказать, определенный я предложил бы на выбор, что сложнее.
Ну тогда
какой-то совсем вот прям какой-то супер красивый там. Они какие-то на экзаменах, по-моему, все скучные довольно, они такие, то, что решабельно за там время. Ну, то есть они редко бывают красивые. Я не испытываю особо какого-то кайфа от экзаменационных задач. Вот бывают красивые, вот, а на экзамене редко такое. Ну, потому что на красивый риск выше попасться. На экзамене обычно такая рутина больше. Вот. Ладно, хорошего настроения. Если есть вопросы, пожелания, комментарии, то всегда пишите. Вот.
Спасибо, до свидания.
Хорошо, спасибо. До свидания.
Да, спасибо, до свидания.
До свидания.